So hopefully I'm frozen. There we go. Hopefully we're starting to get more comfortable with this idea of a parabola. Right? Because in the past, like we talked about in my class in the past, we had only seen equations that give us lines. Right? And now with the parabolas, it's kind of thrown us for a loop because we have equations and things that look like an umbrella or upside down umbrella, right? So different than anything that we've seen before. Now today we're adding on to this stuff with a parabola, okay? All of our parabolas have been in the form y equals a times x squared.
Excuse me, if there are any freshmen who have not had their picture taken or need to have their picture retaken, would you please head up to the auditorium now?
Anybody picture retakes? You guys all did good first try. All of them have been like this. Where has our vertex been for every single parabola that we've looked at? It's been right at 0. Yep, right at 0, 0. Now we've had some that are wider, some that are narrower. We've changed, like, it's not technically the slope, but we've changed the degree of our parabola. But the vertex has been at 0, 0 the whole time. Now some of them have been facing down as well, right? So up or down, but always at 0, 0. Now we're adding this plus c at the end. So we're adding something to the end. And what really all that's going to change is that instead of always being at 0, 0, now it's going to change where our vertex is at. Okay, it's just going to move it around. So warm up, finish our review from yesterday. Our goal today is to be able to graph equations that are in the form y equals ax squared plus c. That's what we're working on, being able to graph. Board of operations, we have our new stuff. Example, and some practice with class game. So the big thing to remember, well, let's backtrack for a second. Who remembers from Algebra? Who remembers from Algebra 1B, so last trimester, looking at functions that look like this, with absolute value? Does anybody remember looking at absolute value? Remember? Absolute value? Right. Yep, so you guys went over some absolute value stuff as well. When we had an absolute value sign, or absolute value stuff, let's say it was minus 7 plus 3. Which part of this told us what was going on with the x values? Inside the absolute value or outside? Maya just said it, I think. Inside, right? And here they told us what was going on with our x values. And with our x values, it gives us minus 7. Does that mean that we are going to the left 7? Yes? You don't remember? It's okay, it's a long time ago. Remember, we would think opposite. So if it said minus 7, that means we were actually adding 7 to the x values when we were moving our graph around. But what about on the outside of the absolute value? That talked about if we were moving up or down. And if it said plus 3, then we were moving 3 up, right? We could trust what was going on the outside of our absolute value sign. It's kind of similar to what we see now. So our equation is in the form y equals ax squared. Now we're adding this plus c. This plus c on the end moves us up or down. And we can trust this plus c. Like it says, c doesn't lie, so do what it says, right? We don't have to think, when we were dealing with the absolute value, we had to do the opposite inside this absolute value sign, and then we had to do the real thing outside the absolute value sign. When we are dealing with this y equals ax squared plus c, the plus c on the outside, if it says plus 5, we're moving 5 up. If it says minus 10, we're moving 10 down. Okay, so we can trust the C at the end. It doesn't lie. We do exactly what it tells us to do. So like I said, the only thing that we're changing today is we are having a C value on the end. That will move our graph either up or down. So we might get a question like this. Graph y equals x squared minus 2. Oh, I forgot to tell you. Get a calculator. Everybody get a calculator right now. Sorry. Commercial break. Get a calculator. Okay, we'll get back to those in a second. But it says graph y equals x squared minus 2. So x equals negative 2, so we need to put negative 2 in for x. Negative 2 squared gives us 4. 4 minus 2 gives us 2. 1 squared is, or negative 1 squared is 1. 1 minus 2 is negative 1. 0 squared is 0. 0 minus negative 2 is negative 2. Negative 1, and we would get 2. So if we were graphing this, we would go negative 2, 2, boom, negative 1, 1, 0, 0. And we could sketch our graph. Okay? That's the first thing it tells us to do is graph. Now, this is a longer table, right? I told you guys we only need to worry about plugging in negative 1, 0, and 1. Now, this is where your this is where your calculator can be kind of helpful. So turn on your calculator and hit the y equals button on the top left. I know some of you have already done this. But in your calculator, hit the y equals. You should see a screen that has a bunch of y's on the left-hand side and equal signs on the left-hand side. Like y equals blank, y equals blank, y equals blank, all the way down. Is that what it is showing you? Perfect. If there's anything in that space, clear it out. So hit y equals, and if there's anything in those spaces, clear it out. So you can clear it just by clear it all out. Make sure there's nothing in there. Are we all there? We good? Okay, go ahead, type in x squared minus 2. And then I want you to, you can hit graph if you want to. Look at the graph, make sure it matches ours. Oh, I totally graphed it wrong. That was on purpose to make sure that you graphed yours right. Negative 1, negative 2, 2 would be here. Here, 0, negative 2 would be down here. There we go. That's a little bit better. Did anybody notice that before I... Anybody notice that? I graphed it wrong? Why didn't you tell me? No, I was seeing if you guys noticed. Well, now I don't know if you did know or not know. All right, I'll believe you. You gotta say something next time. Virtual students would probably notice right away. They're locked into these videos. So that's what our graph should look like. Okay. Now that matches your calculator. Now in your calculator, what I want you to do is hit second and hit graph. So you're hitting table. Second and the graph button, or in the blue should say table. Now if you look at your table, that can be a nice way to help you sketch your graph, right? Because once we start putting like -2 on the ends here, eventually we'll start putting like a 2 in front of the x, and we'll be adding more and more numbers, so it can take longer to plug these x values in. So if you go to your calculator, hit the y equals, put this equation in, and then look at your table, you can easily see, oh, at -2, the x value, the y value is 2. -1, -2, and go through and see your table, okay? Does that make sense? Or have we seen that before? Being able to look at our table and help find those? Okay, good. Just making sure. Did we answer the full question? Graph it. Oh, compare. So if we were comparing, we would say, first what they have in common. Both graphs in this y equals x squared. Just remember a parent function that just goes right here. Right in the middle. Right there. Then you can't see too well. We would say both graphs face up. And then to compare them, to say how they're similar. And then we would say y equals x squared minus 2 is translated. You see this word a lot. When we say something moves on the graph, we say that it's translated. It's translated 2 units down. Right? So on your homework, it's going to ask you a question almost exactly like this, or a few of them, where it says graph the equation, and I would expect to see a little t-chart, and then you have those values in there. So you graph it, and then it asks you to compare. So you say how they're similar, and then you can say a couple things how they're different. In this case, there's only one way that they are different. But in some of the other problems, there might be 2 or 3 ways that the equations are different. What questions do we have before we look at this next example? Does this seem like over the top crazy, or it's just a little bit more than we've been doing? Yeah, hopefully in a lot of ways this is a review, just adding just a little bit more. Which of the following is true when you translate the graph of y equals negative x squared minus 5 to the graph of y equals x squared plus 2? So just based on what we looked at so far, the graph of y equals x squared minus 5, where is that vertex going to be? Right, 5 down. So it'll look something like this. Based on what we've looked at so far, where's the vertex of y equals x squared plus 2 going to be? Someone decide later. What? Yeah, positive 2. So it's going to look something like this. Now it says, how do we get from here to here? How many units do we have to move, and in which direction? 7 units. In which direction, Mark? What? Well, along the y. Yep, 7 units up. So no big deal. The only thing that we need to make sure we keep track of is that we know that we're going from here up to this one, right? Because 7 units down would mean we're going from green to yellow, but that's not what they want. Good job. All right, one more term, one more example, and then we'll look at our class case. A zero of a function, here's our key word. A function f of x, or y equals, is an x value for which f of x equals 0. A 0 is located at the x-intercept. So if we have some type of function, let's say it's a parabola that looks like, no, not like that. That looks like this. The 0 of the function is the x values for which the whole thing equals 0. And it is located on the x-intercept of the graph. This is something that you guys have seen before. And in my class, I know that I showed this during the lecture on a graph. When have we used this? Where have we seen this before? We didn't use the word zeros. A few times I did on accident. I said, what are the zeros? Where have we seen this before? Using these points where our graph goes across the x-axis, or setting our equation equal to 0. Where have we done that? We've all done that before, right? We would set up our brackets. Plus 2 plus 1 equals 0. And what would our x values be? Yeah, -2, -1. We would call these our zeros, like we talked about, and it was only for like a minute or two in my class. But these would be where our graph, this graph right here, crosses the x-axis. We call those our zeros. Notice, and we'll get to this eventually, but these, what do we call these again? What? Well, we call them polynomials. But when we graph them, they're in the shape of a parabola because it's something squared. So when we find the zeros of a polynomial, like we did last chapter, that is finding these zeros on our graph. Okay? Isn't that cool? You guys already knew that, but you didn't know that you already knew that. Is that sweet? Too cool. That's a good way to put it. So the zero of the function, that's our key term. One last example. The function, and this is, one of the real life application problems. The function f of t equals negative 16t squared plus s of 0 gives the approximate height of a falling object t seconds after it is dropped from an initial height of s of 0. So if we are up here, let's say Tad is up here on top of the building, and he has an egg. He drops it, and this building is 64 feet up. Pretty tall building. And we want to know when Tad's egg that he drops is going to hit the ground and splatter. There's the unit. Alright, so that's what this problem is saying. That's what we're looking for. Now we know that Tad is 64 feet above the ground, and it's kind of tricky that the way that they say it, but in this problem they tell us that the initial height, so the height that we start at is represented by s sub 0. How many feet is Tad off the ground? What does it say? 64. So plus 64. Now, what they would be looking for us to do in a question like this, and I know it's a little bit tricky. I mean, how many feet would the egg be when it hits the ground? How many feet off the ground would the egg be when it hits the ground? What? If he has 0. Yep. So what they would look for you to do in a question like this is set this equal to 0. And there's a couple ways that we could solve this. If you plug just negative 16t squared plus 64 into your calculator, into the y equals, why don't you look at the table? So go ahead and do that, what we did earlier. Go to your y equals, clear everything out, put negative 16t squared plus 64, and then go to your table. Get there? Go to your table. That's all right. Now, if we look at our table, let me see it for a second. We want to know when our y value is at 0, right? Because if this whole thing were on a graph, we would be up at 64, and the egg would hit the ground at, when x equals 0, well, maybe not necessarily x equals 0. Y equals 0 here. So what is the value of x when y equals 0? 2. Now, in this problem, they say, a lot of times we've seen f of x instead of f of t, but it's the same thing. F of t just means that we're talking about time. So if this whole thing equals 0, when t equals 2, that would mean that the egg hit the ground after 2 seconds. So Tad dropped the egg from the top of the 64-foot building, and it took 2 seconds for the egg to fall down and hit the ground. Okay? We could, I know you guys didn't love doing this, Algebra 1B. But we could factor out the greatest common factor, write the leftovers, and we could look at what would make this equal to 0. But maybe looking at our table would be a little bit easier. So that would be considered an application question. I know I went over that pretty quickly. And that pulled from a lot of things that we struggled with in Algebra 1B. But we will look at more examples like that in the practice. Do we have any questions